Swift 5.1 is here already, only a few months after Swift 5.0 shipped. As with all Swift updates, there are lots of great new features to help us write better code. This time including opaque return types, improved member-wise initializers, implicit returns from single expression functions, and more. In this video, I'm going to walk you through all the major new features with hands-on code examples so you can see exactly how they work for yourself. Let's get to it. SEO 242 introduces major improvements to one of Swift's most commonly used features, member-wise initializers for structs. In earlier versions of Swift, a member-wise initializer was automatically made to accept parameters matching the properties of a struct, like this: struct user, var name string, var login count, int equals 0. Let Piper equals user, name Piper Chapman, login count 0. In Swift 5.1, this has been enhanced so the member-wise initializer now uses default parameter values for any properties that have them. In the user struct, we've given login count a default value of 0, which means we can either specify it or leave it to the member-wise initializer. Let Gloria equals user name Gloria Mendoza, login count 0. Or let Suzanne equals user name Suzanne Warren. This lets us avoid repeating code, which is always welcome. SEO 255 has removed a small but important inconsistency in the language. Single expression functions that return a value can now remove the return keyword, and Swift will understand it implicitly. In previous versions of Swift, single line closures that returned a value could omit the return keyword because the only line of code that was there must be the one that returned the value. So these two pieces of code were identical. Let doubled 1 equals an array of 123.map $0 times 2. Or let double 2 equals an array of 123.map return $0 times 2. In Swift 5.1, this behavior has now been added to functions as well. If they contain a single expression, effectively a single piece of code that evaluates to a value, then you can leave off the return keyword like this: func double number int returns int number times 2. That will probably cause some people to do a double take at first, but I'm sure it'll become second nature over time. SE68 expands Swift's use of self so it refers to the containing type when used inside classes, structs, and enums. This is particularly useful for dynamic types, where the exact type of something needs to be determined at runtime. As an example, consider this code: class network manager, class var maximum active requests int return 4, func print debug data, print maximum network requests, string interpolation, network manager dot maximum active requests. That declares a static maximum active requests property for a network manager and adds a print debug data method to print the static property. That works fine right now, but when network manager is subclassed, things become more complicated. For example, we might say class throttled network manager inherits from network manager. Override class var maximum active requests is an int return 1. That subclass changes maximum active requests so it allows only one request at a time. But if we call print debug data, it will print out the value from its parent class. Let manager equals throttled network manager. Manager.print debug data. That should print out 1 rather than 4, and that's where SE68 comes in. We can now write self with a capital S to refer to the current type. So we can rewrite print debug data to this: self.maximum active requests. This means self works the same way as it did for protocols in earlier Swift versions. SE0244 adds the concept of opaque types into Swift. An opaque type is one where we're told about what an object can do without specifically knowing what kind of object it is. At first glance, that sounds a lot like a protocol. But opaque return types take the concept of protocols much further. Because they're able to work with associated types, they require the same type to use internally every time, and they allow us to hide implementation details. As an example, if we wanted to launch different kinds of fighters from a rebel base, we might write code like this. Protocol fighter, struct X-wing conforms to fighter, func launch fighter, returns fighter, return X-wing. Then let red5 equals launch fighter. Whoever calls that function knows it will return some sort of fighter, but doesn't know precisely what. As a result, we can add a struct Y-wing that conforms to fighter, or other types, and have any of them be returned. But there's a problem. What if we wanted to check whether a specific fighter was red5? You might think the solution is to make fighter conform to the equatable protocol, so we can use equals equals. However, as soon as you do that, Swift will throw up a particularly dreaded error for the launch fighter function. Protocol fighter can only be used as a generic constraint because it has self or associated type requirements. The self part of that error is what's hitting us here. The equatable protocol has to compare two instances of itself to see whether they're the same. But Swift has no guarantee that the two equatable things are remotely the same. We could be comparing a fighter with an array of integers, for example. Opaque return types solve this problem because even though we just see a protocol being used, internally the Swift compiler knows exactly what that protocol actually resolves to. It knows it's an X-wing, or an array of strings, or whatever. To send back an opaque type, use the keyword sum before your protocol name. From the caller's perspective, that still gets back a fighter, which might be an X-wing, a Y-wing, or something else that conforms to the fighter protocol. But from the compiler's perspective, it knows exactly what's being returned, so it can make sure we follow all the rules correctly. For example, consider a function that returned some equatable, like this. Func makeInt returns some equatable. int.randomin 1 through 10. When we call that, all we know is we'll get back some sort of equatable value. However, if we call it twice, then we can compare the results of those two calls because Swift knows for sure it'll be the same underlying type. We could say, let int1 equals makeInt, and let int2 equals makeInt, then print int1 is equal to int2. The same is not true if we had a second function that returns some equatable, like this. Func makeString returns some equatable. And I'll pass back red. Even though from our perspective, both send us back an equatable type, and we can compare the result of two calls to makeString or two calls to makeInt, Swift won't let us compare the return value of makeString to the return value of makeInt, because it knows comparing a string and an integer doesn't make any sense. An important proviso here is that functions with opaque return types must always return one specific type. If, for example, we try to use bool.random to randomly launch an X-wing or a Y-wing, then Swift will refuse to build our code, because the compiler can no longer tell what will be sent back. You might well think, if we always need to return the same type, why not just write the function as func launch fighter returns X-wing? While that might work sometimes, it creates new problems, such as we end up with types we don't really want to expose to the world. For example, if we used someArray.lazy.drop, we get sent back a lazy drop while sequence, a dedicated and highly specific type from the Swift standard library. All we actually care about is that this thing is a sequence. We don't need to know how Swift's internals work. We also lose the ability to change our mind later on. Making launch fighter return only an X-wing means we can't switch to a different type later on. And given how much Disney relies on the new Star Wars toy sales, that'd be a problem. By returning an opaque type, we can return X-wings today, then move to B-wings in a year. We only ever return one type in any given build of our code, but we can still have the flexibility to change our mind later on. In some respects, all this might sound similar to generics, which also solve the self or associated type requirements problem. Generics allow us to write code like this. Protocol Imperial Fighter has an initializer method. Then struct TIE Fighter conforms to Imperial Fighter, and struct TIE Advanced conforms to Imperial Fighter. Finally, func launch Imperial Fighter is generic over T and Imperial Fighter, and returns a T, then return a new T. So that defines a new protocol that requires conforming types to be initializable with no parameters, defines two structs that conform to that protocol, and creates a generic function to use it all. However, the difference here is that now callers of launch Imperial Fighter are the ones to choose what kind of fighter they get, like this. Let fighter 1 is a TIE Fighter equals launch Imperial Fighter. Or let fighter 2, a TIE Advanced, equals launch Imperial Fighter. If you want callers to be able to select the data type, then generics work well. But if you want the function to decide the return type, then they fall down. So, opaque result types allow us to do several things. First, our functions decide what type of data gets returned, not the caller of those functions. Second, we don't have to worry about self or associated type requirements, because the compiler knows exactly what type is inside. Third, we get to change our minds in the future whenever we need to. And fourth, we don't expose private internal types to the outside world. If you ever forget the difference between protocols and opaque types, think of this. Returning a fighter means returning any sort of fighter type, but we don't know what. Whereas returning some fighter means a specific sort of fighter type, but we still don't know what. In the latter case, the difference is that the underlying type is something specific the compiler knows about. Whereas in the former case, it can literally be anything that conforms to the protocol, even being different every time we call the method. SEO 254 adds the ability to mark subscripts as being static, which means they apply to types rather than instances of types. Static properties and methods are used when one set of values is shared between all instances of a type. For example, if you had one centralized type to store your app settings, you might write code like this. Public enum all settings, private static var values equals a string dictionary, static func get, name string, returns optional string, return values name, static func set, name string to new value optional string, print adjusting name to new value nil coalescing nil, values name equals new value. We could then say all settings.set captain to Gary and all settings.set friend to mooncake. Finally, we could say print all settings.get captain nil coalescing unknown. Wrapping the dictionary inside a type means we can control access more carefully. And using enum with no cases means we can't try to instantiate the type. We can't make a unique instance of settings. With Swift 5.1, we can now use a static subscript instead, allowing us to rewrite our code to this. Public enum new settings, private static var values equals a string dictionary, public static subscript, name string returns optional string, get return values name, set print adjusting name to new value nil coalescing nil. Values name equals new value. Then, new settings captain equals Gary. Or new settings friend equals Mooncake. Print new settings captain nil coalescing unknown. Custom subscripts like this have always been possible for instances of types. This improvement makes static or class subscripts possible too. Swift optionals are implemented as an enum of two cases, some and none. This gave rise to the possibility of confusion if created our own enums had a none case, then wrapped that inside an optional. For example, enum border style, case none, case solid, thickness int. Used as a non-optional, this was always clear. Let border1 is a border style equals .none, print border1. That will print none. But if we use an optional for that enum, if we didn't know what border style to use, then we'd hit problems. Let border2 optional border style equals .none. Print border2. Before Swift 5.1, that printed nil, because Swift assumed .none means the optional's empty rather than an optional with the value border style .none. In Swift 5.1, this confusion now prints a warning. Assuming you mean optional .none, did you mean border style .none instead? This avoids a source compatibility breakage of an error, but at least informs developers their code might not quite mean what they thought. Swift has always been smart enough to handle switch case pattern matching between optionals and non-optionals for strings and integers, but before Swift 5.1, that wasn't extended to enums. Well, in Swift 5.1 we can now use switch case pattern matching to match optional enums with non-optionals, like this. Enum build status, case starting, case in progress, case complete. Let status, optional build status, equals .in progress, switch status, case .in progress, print build is starting, case .complete, print build is complete, default, print some other build status. Swift is able to compare the optional enum directly with the non-optional cases, so that code will print build is starting. SE0240 adds the ability to calculate and apply differences between ordered collections. This could prove particularly interesting for developers who have complex collections and table views, where they want to add and remove lots of items smoothly using animations. The basic principle is straightforward. Swift 5.1 gives the new difference from method that calculates differences between two ordered collections, what items to remove and what items to insert. This can be used with any ordered collection that contains equatable elements. To demonstrate this, we can create an array of scores, calculate the difference from one to the other, then loop over those differences and apply each one to make our two collections the same. Please note, because Swift now ships inside Apple's operating systems, new features like this one must be used with a hash available check to make sure the code's being run on an OS that includes a new functionality. If you're running Xcode 11, you can use hash available iOS 13. Everyone else in older versions of Xcode, you've got to use hash available iOS 9999, a future special version that means we don't know what the actual number is just yet. Anyway, here's the code. Var scores 1 equals an array of 100, 91, 95, 98, 100. Let scores 2 equals 100, 98, 95, 91, 100. Then, if hash available iOS 9999, star, and remember if you're on Xcode 11 you can use iOS 13 there. Let diff equals scores 2 . Difference from scores 1. for change in diff, switch change, case.remove, let offset underscore underscore, scores1.remove at offset, case.insert, let offset, let element underscore, scores1.insert element at offset, and finally print scores1. For more advanced animations, you can use the third value of the changes, associated with. So rather than using .insert, let offset, let element underscore, you might write .insert, let offset, let element, let associated with instead. This lets you track pairs of changes at the same time. Moving an item down 2 places in your collection is a removal, then an insertion. But the associated with value ties those 2 changes together so you can treat it as a move instead. Rather than applying changes by hand, you can apply the whole collection using a new applying method like this. If hash available iOS 9999, comma star, let diff equals scores2.difference from scores1. Let result equals scores1.applying diff, nil coalescing, an empty array. SE0245 adds a new initializer for arrays that doesn't pre-fill values with a default. This was previously available as a private API, which meant Xcode wouldn't list it in its code completion, but you could still use it if you wanted to, and if you're happy to take the risk that it will be withdrawn in the future. To use the initializer, tell it the capacity you want, then provide a closure to fill in the values however you need. Your closure will be given an unsafe, mutable buffer pointer where you can write your values, as well as an in-out second parameter that lets you report back how many values you actually used. For example, we could make an array of 10 random integers like this. Let random numbers equals an integer array with the unsafe initialized capacity of 10, buffer initialized count in, for x in 0 up to 10, buffer x equals int.random in 0 through 10. And finally, initialized count equals 10. There are some important rules here. First, you don't need to use all the capacity you asked for, but you can't go over capacity. So, if you ask for a capacity of 10, you can set initialized count to 0 through 10, but not 11. Second, if you don't initialize elements that end up being in your array, for example, if you set initialized count to 5, but don't actually provide values for elements 0 through 4, they're likely to be filled with random data. This is a very bad idea. And third, if you don't set initialized count, it will be 0. So any data you assigned will be lost. Now we could have written our code using map like this. Let random numbers 2 equals 0 through 9 dot map underscore in int.random in 0 through 10. That's certainly easier to read, but it's less efficient. It creates a range, creates a new empty array, sizes it up to the correct amount, loops over the range, and calls a closure once for each range item. So as you've seen, there are lots of great new features coming in Swift 5.1. But which ones are you most looking forward to using? Let me know in the comments below. And if you enjoyed this video, don't forget to subscribe to my channel. I make lots more videos like this one to help you improve your skills as a Swift developer.